OK. Bon. Ouais. Xavier Gomez-Montt, of the CIMAT. Ah oui. Of the CIMAT. Non, vous prenez les lunettes. We'll speak on geometry and dynamics of holomorphic flow.
Okay, thank you very much. I would like to begin by saying some personal remarks. So when I finished my PhD in Princeton, I returned to Mexico and I wanted to find my place in the world. And so I was very fortunate to go to a meeting first in Trieste and then just afterwards to Creta, where I met these two beautiful persons that we have here in front, César Camacho and Robert Moussu, which in some sense they have been the leaders of a group, which I think we are all part of this group. So I feel like if we are tribe men, and they are our guides in this path. And about César in particular, I admire many things. The first thing is what we call in Spanish el buen gusto, el gusto. I think Dominico also said it by saying the class. He has lots of class, so he has muy buen gusto, très bon goût, très bon goût, in the sense that mathematics is full of technicisms. And many people get lost in technicisms, and somehow during his many expositions and his written works, he has shown us how to avoid getting into this pitfall. So I admire very much his bon goût. Also, I admire his, I'll say it in Spanish because I don't know how to say it in English, astucia. He's muy astuto. So in that sense, he goes into a place, he sees where the thing is, and he is very eficaz. I don't know how you say that in English. So that also I admire very much of him, that he could get into a situation, see where the good thing was, and he just lost no time and directly went to pick it up, and when everybody else realized, I mean, he had already published it. So, but anyway, and also I admire in him his devotion to mathematics. I think he's a very devoted person. He one can feel the mysticism in his way he does mathematics, and I think that has permeated to all the group. And as also Dominique observed in the morning, for some reason or other, his most renowned theorem is this separatrix theorem. And as you know, separatrix comes from the real case that a curve that passes through the origin separates the plane into pieces. And so people were finding separatrices because you could separate the dynamics into different blocks. So in that case, I call this the miracle of the separatrix. You know, it's this theorem that he found with Paulo Sad. And so I wanted to bring something to him, which was like the counterpart to this. And so this is this I call is the miracle of the union trees, because this is not the separatrix but the union tree. So this is like the counterpart, and it's a theorem that was discovered in Mexico many years ago in 16th century. And I'll say it first in Spanish. The theorem says is the following thing. It says la madre de Dios es morena. So this says the following thing is that the mother of the Western God is non-Western. So this is a gift I bring to him.
Muchas gracias, muchas gracias.
And it was built by our Indian persons. It's an aircraft from Michoacán. And so I'll speak about mathematics now. So also this mathematics that I'm going to speak is very much influenced by this fortunate situation I had of being in contact with IMPA and with Dijon. And the work I'm going to speak about is I've been working on this for the last 3 or 4 years. And at the beginning it was only a dream. And thanks to my collaborators, this dream has been materializing into some concrete theorems. And so let me explain that context. So we begin with the Riemann sphere minus a finite number of points and a representation into a PGL NC. And then from this, we're going to construct a polynomial vector field, which is called the Riccati equation, whose monodromy, I'm going to explain, monodromy is given by this row. And so once I explain what is this object, so the problem here is to understand what the leaves are doing, which is, I think, one of the basic geometric thing we want to understand of the foliation, what the leaves are doing. But before explaining this, let me go to the real picture, to some real picture. So here we have M is some real manifold, and we have X, a vector field. And then from this, we get the flow, of the vector field. And so, as we all know, so the manifold gets foliated into these one-dimensional leaves. Perhaps there are some critical points. And it's a very classical problem to try to understand here exactly what are the leaves doing here. Now, lately, there has been a lot of work on these things which are called SRB measures, which I learned in my participation in congresses here in IMPA. And it means the following thing. See, it demands like a change of a point of view, in the sense that one is tempted to use this Cauchy approach, which means the following thing. You give an initial condition, so you give me a point on the leaf, and then you want to figure out what is the leaf which is passing through that point. But when the leaf is very complicated, this is a very stupid point of view, because it's going to depend very much on which point you chose. If you move a little bit, then it's going to be, at the beginning they're going to be very close, but after some moment they're going to be completely different apart. So in that sense, the problem is very sensitive to initial conditions. And so this, what it says is that to this problem, one should look, it says look for measure mu, a probability measure mu on the space M in such a way, so if we take here some open set, say some open set U, in such a way that mu of U, which is going to be a number, say 0.17, is going to be the percentage of the time that you're going to be spending, that the general orbit spends in this open set. So this is going to be equal to, so you take the set of points P in 0n in such a way that phi t of the point P0 is in U, you divide by n. So this is the average time that your initial condition P0 spent on the region U divided by the n, and then you take the limit when n tends to infinity, and you want this to be true for almost every point P0 in the sense of Lebesgue. So it might be very difficult to say where is this point going to be in 5 hours. But you know that this point is going to spend 0.17% of its time in this region. So this is like something that one has learned from modern theory of dynamical systems, that to understand complicated systems, this is a good idea. Or this is what they sell here in IMPA. That this is a good idea. And so I believed, you know, I'm a believer, and so I say, I believe. But, you know, my mind is complex. So in some sense, the question is, what is the analog thing in the complex situation to these measures over here? So if we have here now M is a complex manifold, and F is a foliation by curves with singularities. So in the case I'm going to describe, this is given by a polynomial vector field in C bar cross CPN. But we have this, so we have our manifold, and now we have these two-dimensional leaves. Now in this case, the real people had it easier in the sense that in this universe that we live on, we think that time is one-dimensional, and we get this idea, and this seems to be like a very natural idea for us human beings. Now, if we're here, so we'd like to say, what is the equivalent thing to this situation? So in the real case, they were very fortunate in the sense that the orbit is canonically parameterized by the real numbers. Now, here, as we know, when we begin to understand this topic, is that the leaves, even though the equation is locally solved by the complex numbers, if you do it in C2, very quickly you arrive at infinity, and then you have to renormalize, you have to multiply by a factor and bring what's happening at infinity here, but it's a pole, so you multiply by a denominator, and in practice you lose time. If not your full life, you lose time. And so there is no canonical parametrization because you have to normalize, and then it doesn't work, and this very nice idea, it doesn't work, okay? So, but on the other hand, we are very fortunate because we have this theorem of this Poincaré-Keb, the Poincaré-Keb uniformization theorem that says that most Riemann surfaces are covered by the unit disk and that the conformal group of the unit disk is equal to the set of isometries of D with the hyperbolic metric. And so that means that most of the Riemann surfaces have a canonical structure of a hyperbolic, have a canonical Riemannian metric of constant curvature -1. Now, Marco Brunella has been explaining in several of his works that either all leaves are parabolic or the set of parabolic leaves is a pluripolar set, which means in particular that it has measure 0. Now, this approach from real dynamical systems also says, see, here is that you are allowed to throw out an exceptional set of measure 0. That is permissible, it is necessary. If you want to understand everything, you can't. You can't understand everything. So if you can forget a countable a set of measure 0, and so in that sense we may assume, or we may assume that this foliation by curves has the property that its leaves are hyperbolic. Most of its leaves are hyperbolic, or it has one hyperbolic leaf, and then most of the leaves are going to be hyperbolic. That's what, thanks to Marco, we can say that. And so in our context we can do this. And so a way to replace these kind of measures then would be the following thing. So we take a point P0, we take the leaf passing through the point P0, and we take its uniformization by the unit disk, phi. So phi from the unit disk into L of P0 is the uniformization. So, for example, if the leaf is simply connected, then this is just a parametrization of the leaf. Now, so which is sending 0 to the point P0. Now, we take here a disk of radius 0 and radius n. And here we put, so the Riemannian metric, the area of the disk, of this finite disk. So this is the area element over here, and we divide by the total area, a number, the area of this disk. Excuse me? No, Poincaré area. So we put the Poincaré area in this disk, so the Poincaré area element, and we divide by the total area. So this is a probability measure. This is a probability measure. So this is assigning, so what is this, if we call this measure mu of the point C0 or 0, because we're in the disk in radius n. So if you measure a set with respect to this, it will tell you, first you would have to intersect it with this disk, and then it will tell you what is the relative area compared to this disk of radius n. Now, with this phi, we push this measure over here. So we're pushing this, so we have phi lower star of this mu 0n. So here, the uniformization was sending the point 0 to the original point P0. And so this is a probability measure. So from the point of view of the foliation, if we take an open set or some measurable set, and we say, what is this number? So this would say, this would intersect this with the support of the measure, which would be this image of the disk, and it would say which is the percentage of the time that the disk is passing through this open set. And then we take the limit when n tends to infinity of this measure, and so we want this to exist, so that there exists a measure in the space which is telling us what is the percentage of the time that the leaf is passing through that set when we are measuring time with respect to the hyperbolic area, which is something which is canonical to the conformal structure of the leaf. So this is, I think, the equivalent thing to this real picture over here. And so in the complex case, when they tell us solve the differential equation, one is tempted to do it in the Cauchy way. You give me the initial condition and I tell you the expression, which, and these guys are telling us, no, you don't do it like that. You do it some other way. Why? In the first thing is that, see, this measure over here is going to be the same for almost everyone. So you only have to give one answer. There is not an answer for each initial condition. There is just one answer. So in that sense, the claim is the following. If you give me a polynomial vector field in C2, there is a measure associated to this polynomial vector field. And in some sense, this measure, from this point of view, is the solution to the polynomial vector field. You don't do this of, you take the leaf and you follow the leaf and you do analytic. No. It's something else. So that's what, you know, in these congresses in IMPA or in Trieste, they have different sessions, and so you go to different rooms, and one thinks that usually people which are listening are not hearing, but even though I sleep most of the time during the lectures, something stays. So, something remains. There's a residue, the residue theorem. And so, so we have this measure. So the thing is, it looks nice, but now prove to me that there is something like this. Okay. So the result that we have is that putting a generic hypothesis on the representation, we can prove that there exists this measure. And actually, I had been thinking on this problem because I had learned from Ricardo Magné this theorem of Osseledek, and I said, gee, I was very impressed with the statement of the theorem, and I said, I need to apply it to this situation, which looked very much that it could be applied. And so once I spoke to Christian Bonatti that was visiting Guanajuato. We were walking in the mountains, and he told me, what other problem you're working on, because we were working on something else. And I said, oh, look, have this representation, you have this measure, there's this measure. And usually when I spoke to anyone about this, they won't understand. You know, you get this look that people say that you're crazy. But I was very fortunate with Christian because he not only understood me on the spot, but immediately gave the next step and told me there is an attractor. And I said, which attractor? So it took me like another 6 months to understand the attractor which Christian showed me. So now I have this problem of showing you that here there is an attractor. And this attractor is this measure that we're going to construct. And it's a hard task because in some sense you look at this hypothesis and you say, I don't see the attractor. But there is an attractor here, and I will try to convince you of this attractor. So this attractor is going to be this measure, but it's a complicated attractor in the sense that one is used to having, if you have I mean, this is like an attractor, right? Everybody goes there, no? But that's like a stupid attractor. A more interesting attractor that we're going to use is the following attractor. So here in this case, I put as my basic hypothesis, so this is a Riemann surface minus R, with R bigger than or equal to 3 points, so that it's hyperbolic. But actually here I could have put any compact Riemann surface minus a finite number of points, which is hyperbolic. So genus 1 with 1 point deleted, at least 1 point, or genus 2. And so another thing I learned and that we're going to use is the following. So this is like the first attractor, the first non-stupid attractor. So here we have this Riemann surface over here. And so the punctures in the hyperbolic metric, they go like this. And now we want to understand, so here we put in on let's call this S. On S, we put the hyperbolic metric. And we want to get the geodesic flow here going on. So what does that mean? See, if you give me a point and a vector, then there is a unique geodesic which is going to be and it's going to be doing like this. So given any point and any direction, there is a unique geodesic starting at this point with this direction. So this means that if you give me just a point and you say get going, you don't know where to go because you say which direction. So this means that the geodesic flow does not live on this surface. It lives on the unit tangent bundle of the surface. So this means that you have to give a point and you have to put a direction. Or what I call is you have to have a compass. So you have these compasses that follow the magnetic, and so you follow in this direction, and so you walk with your compass, and then you know how to flow. If you lose the compass, you don't know. But so this means that, see, we have to go to the unit tangent bundle of the surface and cross R into the unit tangent bundle of the surface, and here's where we have the geodesic flow. The geodesic flow does not live on the surface. So this means the following thing is that to do what I'm going to do, we will have to introduce an additional variable that in complex variable nobody does. So this is like a new idea here is that to this polynomial equation, we're going to add a new variable, which is this compass. And then to this compass, we're going to get something which is going to be called the foliated geodesic flow. On a foliation, and if the leaf has a hyperbolic structure, and they say you take a point and you say flow, you will know in which direction. So you add this new direction. Now, in the end, we will have to forget this new direction and we have to pay a price. So we put in the new variable, we do an argument, and then we have to erase it. But if we don't bring it in, we can't do the argument. Okay? So this is the geodesic flow. Now here, the impressive theorem is this Hobbes ergodicity theorem. So in the unit tangent bundle of S, we have a volume form which essentially is equal to the area form cross d theta. So d theta is the angular measure because it's a group, so it's just the hard measure on the theta, normalized so that it has area 1. And so Hopf's ergodicity theorem says the following. For me, when I found it, I first read it, very remarkable theorem which says the following thing. You take an open set here U in the unit tangent bundle of S, and you ask how frequently does the geodesic pass through this open set. And so it turns out that the percentage of the time that the general geodesic passes through this open set is the area of this open set. So this means that the Liouville, so this is called the Liouville measure. Liouville measure. So if you consider the differential equation associated to the geodesic flow on this finite Riemann surface, so it has finite volume. And so this SRB measure, which I was calling for the geodesic flow, is exactly equal to this Liouville measure. So in some sense, here is something very remarkable, which I think these ideas originally came from Boltzmann, and the physicists thought he was crazy, is how to fill something two-dimensional with a one-dimensional thing. Voila. So in this sense, Hopf's ergodicity theorem says that if you take the limit when t tends to infinity of 1 over t of the length, so this would be the length of the set of points t between 0 and t in such a way that phi t of the point p0 belongs to a set U is equal to the integral of over U of the Liouville, and this is for almost every initial condition with respect to the Lebesgue to the Liouville measure, to Lebesgue volume in this manifold. And so this is the first example of a non-trivial attractor. So you have to see here, there is an attractor here. Who is the attractor? The attractor is this Liouville measure. And so another way of viewing this is the following thing. If you go to the space of measures, probability measures, in this space T1 of S, and if you take here an arbitrary measure mu0, I don't know if this is an arbitrary or a general measure here, mu0, and you do phi t lower star of mu0, and you take the limit when t tends to infinity of this measure, this is going to go goes to the Liouville measure. So if you push a measure with the geodesic flow, you are going to go to this Liouville measure. So in that sense, the attractor is not in the original space, but in this measure, in the space of measures. I think this is correct. No, Alcides? You were asleep when Mañé. So this is more or less the picture. So now let me go to my to the situation here we have at hand. So here, so I'm going to take a representation into GLNC. And so what this means is the following thing. So we have a Riemann surface minus a finite number of points. And so this is a canonical construction, which is called the suspension of the representation, which I'm not going to explain in much detail, which means the following thing is that you take the universal covering space cross Cn, and in here you take this trivial foliation like this, and then you act on the first, so the fundamental group is going to act on the first factor is by covering transformations, and on the second factor is going to act according to the representation. And so in the end what we get is a vector bundle over the punctured Riemann surface with, and so here this corresponds to a flat connection, and so here corresponds to a foliation which is transverse to the fibers, a foliation transverse to the fibers, and then we can compactify if we want. We can go over the punctures and put a linear model to get something in C bar cross CPN if we want. So here we have a foliation in C bar cross CPN, and then this foliation, I'm sorry, in CN. And so this foliation looks like this. It looks like dW1 over dZ, dWn over dZ, equal to, and here we have a matrix Aij of Z, W1, Wn. So this is a linear ordinary differential equations with variable coefficients. Given, and the poles of these Aij's are located in the points we deleted, and conversely, given any equation of this form, there corresponds a representation which is called the monodromic representation, which was discovered by Riemann more than 150 years ago. The monodromic representation, and so there is an equivalence between that kinds of representation and these kinds of equations, and we're trying to understand these kind of equations and what are the solutions of these equations doing. Here these ij's of sets are rational functions. That's why when we get rid of the denominators we get a polynomial differential equation. So this is a special class of polynomial differential equations which is linear in many variables and is nonlinear in this special variable. So it's a combination of linear and nonlinear equations, and we get this representation. Now, so what this means is here we have this C bar minus the points, P1, PR, I don't know how I call them. So, and here we have the foliation which is going like this. Now, so if the base surface is a hyperbolic Riemann surface, all the leaves are going to be hyperbolic Riemann surfaces because they are on the way, they are covering surface of this. And so if you have a hyperbolic thing and you have a covering surface in the middle, it's also hyperbolic. So, and actually the metric, the canonical metric, is obtained by pulling back the canonical metric here to the leaves of the foliation. So this is a case where the Poincaré metric actually varies real analytically with respect to the leaves. You can move from leaf to leaf and it's real analytic. So I'm going to leave this because this is my basic assumption. Now, so let me show you where is the attractor. No, this is the where is the attractor? So we're going to introduce this new variable, and we're going to go to the unit tangent bundle of S. S is this puncture thing. This is tangent bundle of S, and so here we have this this bundle E of rho, which is the bundle with fiber Cn, living over this. So this constructs a bundle over this, and here we take the unit tangent bundle of S. Let's call this pi, and so we call the pullback of this bundle, let's call it pi of E. So we have here a pi star of E rho. And so here we have a foliation by real three-dimensional leaves. And so a point here corresponds to the usual foliation over here. So here we have the foliation to give a point and a direction. And so given a point in a leaf and a vector tangent to the leaf, we can get the geodesic beginning at this point and going in this direction. And we can move time t. And so this means that here we're going to get phi sub t is the foliated geodesic flow. And over here, down here, we have phi, which is the geodesic flow. So this is a flow which is living on top of this. So that means if we take a point and a vector, so here we have our thing like this. So we start moving like this, and we're going to be moving. And so here we have the geodesic, it's going in like this. Here we're going to be, as I mentioned, by Hopf theorems, traveling everywhere. But here, when I'm going to change from one point to the other according to the representation. So even if here I see that my path is coming back, then I have to take what is the homotopy class of this coming back. So I take this loop. So if I begin here, and I'm coming back and I'm around here, I close by a short curve, and I take the homotopy class corresponding to this. I push with the representation, and this will tell me where this initial condition is moving on the line over on the fiber over here. So the dynamics of the differential equation is a combination of the geodesic flow downstairs and the representation, and we have this gain. Okay, now so we take a geodesic. So we take a geodesic and we expand it like this. We expand it like this. But let me say, see, the miracle is going to be the following. Here there is a miracle. Is the following. You take a point and a direction. So an element here, and I tell you choose an initial condition. And so here you have a copy of Cn, and you say any point there looks to me the same. Which initial? So here I have my vector v at the point z, and here I have to choose vz and then a w0. An initial condition in the Cn. And one says any initial condition is the same. No. There is a favorite initial condition. And you say, a favorite initial condition? To me, all points in Cn look exactly the same. So why should there be a favorite initial condition? So this is the origin of the attractor. So the origin of the attractor here in this equation, which in the end is the reason why this mu is going to exist for this kind of equations, is exactly the fact that there is going to be a favorite initial condition. Okay? So you say, gee, where's so the favorite, we are here in time 0, and here we have our Cn. Now, the thing is the following, is that we say, you don't choose your initial condition now. You choose your initial condition when the dinosaurs were around. So you go to minus 10 to the 10, okay? Now, here is where you have, here you have your Cn. And here you're going to choose your initial condition, W0 tilde. Now, what happens as you move along here? Well, if we look at the universal covering space, and we'll look at the fundamental region, it looks something like this. And then we do this Escher kind diagram, and we have this tessellation of the universal disk. And we're taking a geodesic here. Now, every time we move from one fundamental region to the other fundamental region, so here we take alpha 1 up to alpha r minus 1. This is a free group. The generators are going around each one of these points except the last one. And so this corresponds to some matrices. So this means that on the vertical fiber, we have to be multiplying these matrices according to how we change fundamental regions, how the geodesic that we chose changes fundamental regions. So this means that to do this, every time we change a fundamental region, we have to apply one of these matrices or its inverse. And so we're doing lots of multiplications of these matrices, okay? Now, so this is an idea which I learned from Oseledek theorem. It's not that I'm very brilliant. It's that I sometimes are awake during the lectures. So you take a sphere and you apply this sphere by the linear map. And the claim is that this is going to be a very elongated ellipse. Why? See? Well, suppose in the middle of the way we have here some elongated ellipse like this. Now, what do we have to do to make this ellipsoid be round again? So we have to start hitting it with the most contracting transformation exactly in the most expanding direction. Now, if you have several matrices which are in some sense independent, so I have to put a condition on these matrices which guarantee this independence, the probability that the next matrix will be hitting exactly at the point where I need it is almost zero. And so if I do several of these, what happens is that the ellipsoid will just turn around, but anyway, it will be a very elongated ellipse. Now, if instead of beginning at the time when the dinosaurs were around, we begin in the time when the Earth was beginning to be formed, okay, and we take the initial condition here. So here's where we take our initial condition. Then the map from here to here will be one of these elongated ellipses. And so anyway, here I put equivalent distribution to the choice. Here the probability will be centered in this direction. And so anyway, when I push this over here, it's still going to be in this most elongated direction. So what one has to show is the following. So one has to define something which is called, which I also learned in these IMPA meetings, these Lyapunov exponents. Look at the Lyapunov exponents. So one has to figure out if we can decompose this bundle over here. This is a vector bundle. So we want to decompose this as E lambda 1 plus E lambda r with lambda 1 real numbers bigger than lambda r in such a way that if you take the Euclidean norm on this, so you put some Hermitian norm on this bundle over here. There are some technical things which I'm not saying that, for example, there are these punctures, so how does this depend on the Hermitian form? But anyway, one has to be smart and deal with these problems. But as I said, I have some very smart collaborators, so don't worry. So the thing is over here. If you take a vector v, which is in one of these E lambda j's, then if you get phi, this big phi at this vp with this initial condition b, and so this is the initial condition and this is the time t, and then you take the norm and you take the logarithm of this and you take 1 over t and you take the limit when t tends to plus or minus infinity. This is equal to lambda j. So this means that the rate of growth forward, you're going to have exponential rate lambda j, and backward minus lambda j. Okay? And so to make this thing march go in the case of the attractor is the following thing, is that the dimension of the E lambda 1, so that the dimension of the biggest growth of the Lyapunov exponent is 1. Because then it tells you that when you march, there is one direction which is growing much more than the rest. And so that means that as you march, you're going to be always looking in that direction. And so when they say choose an initial condition, you're going to say, I'm going to choose the initial condition given by the most expanding direction. Okay? So now, so what's the hypothesis? One needs to guarantee this is a condition on the representation. So the condition star is that, so these matrices A1, the generators or the full group, the monodromy group, A1 up to AR minus 1, induce transformations on CPN minus 1 to CPN minus 1. So linear transformations induce transformations in projective spaces, and one asks that there does not exist a probability measure invariant by this A1 up to AR. But by the group generated by them or by the generators, is the same. So, for example, if they have a common eigenvalue, then you have a Dirac delta on that point. That is not allowed. They cannot be all Hermitian. So we are avoiding the case of abelian. For example, if it's an abelian, if they commute, no. Because if they commute, then there is this question about, you know, if you're tossing a coin, you're tossing several coins, no? One in reales, one in pesos, one in dollars, one in euros, no? And you start doing this game, that's what we're doing, no? Several of these, no? And you say, let's play like this. Probability theory says that if they are fair coins, in the average, you're going to be 0, even. But then what this means, if you look at it from the point of view of the spheres, is that you're going to be coming back to the round sphere. So we are using, in an essential way, the non-abelianness of the matrices. If the matrices commute, what we're saying doesn't work. There does not exist a most expanding direction, because often you're coming to a situation where you don't have a most expanding. But if your matrices do not have this property, then one can prove that you do have this thing over here. Okay, so under this hypothesis, then we have this hypothesis imply. So for general considerations, as I mentioned, of Osseledek theorem, one has this, there is this measurable decomposition of this vector bundle, and there are these eigenvalue, these Lyapunov exponents, which are the same for almost every initial condition B. That's Osseledek theorem. And so one has to use this condition to prove that the most expanding has dimension 1. And so now we, instead of considering the equation we take the projective bundle associated to pi lower star of E rho. And here we are on the tangent bundle of S. And so this is now a CPN minus 1 bundle over this unit tangent bundle of S. And the representation we have in this case, once we projectivize, is to the projective linear group. Now, here we have the geodesic flow. Here we have also this, we have also here a foliation by three-dimensional leaves. We have this foliated geodesic flow. So in this case, these linear differential equations, once you projectivize, becomes the Riccati equation. That's the name, the Riccati equation. So that's why this is the Riccati equation. And so what this proves is that there is something which is called a sigma plus, which is choosing the most expanding. Now, see what happens. So here we have this T1 of S, and here we have this ergodic flow, geodesic flow. Now, if you choose an initial condition, here we're in projective space, so we have this vector. Now, any vector, if you march along this geodesic, will get close to this because this is the most expanding direction. So this means that for these all initial conditions, which begin over the same point, when you march according to the geodesic flow to this, you're going to get close because of this most expanding direction. So this is going to get close like this. But now, if you look at this is wandering all over the space over here. So this means that we can construct here a measure mu plus, which is equal to, and so we take the Liouville, we push forward with this section of most expanding, which is most expanding, we push forward the Liouville measure, and one can prove that this measure over here is an Sinaï-Rouel-Bowen measure for this real flow, which means that the statistics of most geodesics over here is tending towards this measure over here. And now what we have to do is to project now this measure over here. Now here we are on S, and here we're in Proche of E rho. So here's where we have our holomorphic foliation given by this Riccati equation. And so we obtain this mu, which is equal to, we call this projection pi, we called it. So this is, mu is pi lower star of mu plus. And then the claim is that this measure is the measure which has the statistical properties which I mentioned in the beginning for the Riccati equation. Here, in some sense, what's surprising over here in this situation over here is the following. See, is that you say, look, if I go in this direction, you say, I'm going to go to Japan, no? And if I go to the other direction, I'm going to go to the North Pole, no? So you might think that if you go in different directions, so instead of going all the way through the leaf, what we're saying, take one direction and march, and march, and march, and march, and march. You're going to see the same thing. I mean, so you say, you march this direction, and you march the other direction, and we communicate with our cellular telephone, and you say, what are you seeing? And in the average, I mean, you say, look, I'm in New York now, and you, well, you know, I'm in Amsterdam. But in the average, you say, how much time did you spend in New York? And say, 0.015, and the other, 0.015. How much in Paris? No, 0.13, 0.13. So it's very surprising. Because you're not following the other. I mean, if it's a stupid flow and everybody is flowing like this, it's easy. But everybody is going in the itineraries are completely different. But on the average, they are visiting the same place. So the flow already, so here this flow, the foliated geodesic flow, already has statistics. This statistic is obtained from a combination of Hopf ergodicity theorem plus these Lyapunov exponents. And then when we project over here, the thing is the following, is that you might say, well, if in this direction I'm seeing the same thing, and in all these directions I'm seeing the same thing, it looks like very natural that in the disk I'm looking at the same things. But there is a trick in the sense that it is true that for most directions you're seeing the most thing, but also periodic orbits are dense. Periodic orbits, you're doing just a finite combination and repeating, and so the eigenvalues are not the same. So that argument doesn't work, and instead of considering the foliated geodesic flow, one has to use the horocycle foliated flow, and one uses the fact that horocycles is uniquely ergodic, not only ergodic, but uniquely ergodic, and that the orbits of the horocycles look very much like large circles. So there is an additional extra work that, so here it looks like this is, yeah, you just descend from here to here, but one has to do some extra work. And so this work I have been doing during the last couple of years with Bonatti, with Obiana, and with Villa. And in a sense, well, you can see Dijon and IMPA in action. They have helped me with the muscles. Okay, thank you very much.
Antes no había entendido